Good morning, everyone. Are we on? Good. Very excited to be here. Happy to be kicking off this event. I've been really impressed with the other teams that are here with me all the past 2 days, and so I think we're in for a very exciting conference. With that, I want to talk to you about robots. And if I asked you to picture a robot, you'd probably picture something like Star Wars' C-3PO. And that's because that's what the history of robotics has looked like. But if I asked you to think of the future of robotics, you might take a very different vision. Maybe you'd picture something like Westworld's lifelike robotic, which could even be a threat to humanity. But instead of thinking of how the rise of technology and robotics will lead to our downfall, I want you to imagine how robotics can empower us, even lead to the next stage of evolution. Because when I think of a robot, I think of so much more than a vacuum cleaner for my home. I think of a prosthetic device to help enhance someone's quality of life. I think of a healthcare robot, so my grandmother doesn't need to live in a nursing home. She can maintain her autonomy. And I think of an agricultural robot to help feed our growing population and remove the lowest paying jobs. With this beautiful vision of a robotic future, you should not be asking yourself if this will happen, but when and how. I'm Tim Morrissey, co-founder and CEO of Artimus Robotics, and today I'm here to talk to you about the future of robotic motion. Let's take a look at what's going on in robotics today. This is Honda's Asimo, and if you remove its friendly covering, you start to get an idea of why you and I don't own an Asimo yet. It's comprised of metal gears and motors. These are heavy, complicated, inefficient, making the device expensive. This product apparently costs $2.5 million to make. And has anyone seen Asimo in the news recently? Honda just announced it's ending the Asimo project. And so if a major corporation like Honda can't figure out consumer robotics, maybe it's time we take a different approach. Maybe instead of using gears and motors, we use something more elegant, something inspired by nature. The natural muscle is an incredible device. It can be very strong, fast, it's adaptable. My team at the University of Colorado Boulder set off to try to recreate this technology. We tried to make an ultra-versatile artificial muscle. We took an old science and applied it in a radically new way to introduce Hazel artificial muscles. Hazel stands for hydraulically amplified, self-healing, electrostatic artificial muscles. And I'd love to show you what we can do with it. Hazel can operate like a bicep with precise motion, fluidic continuous motion, and rapid motion. Hazel, because of its capacitive nature, can be self-sensing. So with the same two wires, you can both actuate and sense position. Because of its self-healing characteristics, you can scale Hazel up and start to do real-world tasks. It's powerful enough to jump off the ground, yet delicate enough to handle simple tasks like picking a ripe raspberry. We released this work earlier this year, and the response was fantastic. Hazel, a true breakthrough in actuator technology, national and global press coverage. And I think the reason for this was because of how elegant and beautiful the solution really is. There's 3 key components in a Hazel actuator. There's an electrode to conduct electricity. There's a stretchable or flexible shell, like a thin plastic film. And there's a liquid dielectric, which is inherently self-healing because of that liquid property. The first liquid dielectric we ever used was actually just canola oil from the local grocery store. To operate a Hazel, we'll apply a voltage, which introduces a Maxwell stress that acts on the liquid dielectric. This will locally displace hydraulic fluid and drive a shape change in the soft structure. I told you earlier we set off to recreate the performance of natural muscle. How do we do? Well, if you look at that hummingbird, it flaps its wings about 10 to 80 hertz. Hazel operates above 100 hertz without reducing its strain. For strength, a great performance characteristic is the power to weight ratio. Natural muscle, 50 watts per kilogram average, 300 peak. Hazel beats it by nearly an order of magnitude in both. And adaptability, I already showed you adaptability. With that same structure, we can design all sorts of devices. Devices for jumping, for gripping, for linear motion. But don't be excited about where Hazel is today. Be excited about where we're going. The incumbent technology, such as a servo motor, has been around for over 100 years, with a key performance characteristic of a power-to-weight ratio in the tens to hundreds watts per kilogram. In just the 3 years since Hazel's been worked on, we've already exceeded this performance characteristic. This trend is true across the board in key actuator performance, efficiency, speed. Where we're going is quite astonishing. So I've talked a lot about actuators, linear motors, servo motors, Hazel actuators. Where are these actually used? Well, in those robots I opened with, these would be your legs, your arms, your hands. But actuators are everywhere. If you took an automobile to get here today, you've already used actuators. In a car, those are going to be your locks. They're used for fluid regulation. They're used for brakes. But these are complicated industries, both robotics and automotives. Take the example of the consumer robot. There are many, many parts in this. And Artimus Robotics, we're not going to make a consumer robotic today. We're a new startup. We're not even a year old. We're going to provide the components and sub-assemblies that get incorporated into the next generation of robotics. We want to sell to the Boston Dynamics, the Misty Robotics, to help them get this lifelike motion. That's for a few reasons. First, that's where our IP lives. We have 2 provisional patents, 1 recently converted to a PCT, and a 3rd one in the works. But also, by producing linear actuators, really no industry is off limits to us. That same linear actuator that goes into a gripper for the consumer robot can go into a pump for manufacturing and healthcare, or it can be used for a haptic surface in automobiles and vehicles. I don't know how many actuators there are on the space station. I would guess it's in the thousands or tens of thousands. Those are all made out of metal. Metal's dense, metal's heavy. Our actuators are more lightweight, cheaper to get it up there. And for consumer electronics, there's a lot going on in this space for haptics. One company I already heard you're familiar with, Semitic Labs, just moved to Denver. We actually met them at the Ignite the Night event earlier this year, and they even provided us with a letter of support for a Colorado AIA grant we just applied to. But we're not just talking to startups. We're talking to major players as well. Microsoft, Google X, Mercedes-Benz. They've all reached out to us to learn about our technology. And our academic research team, the Keplinger Research Group, already has proven we know how to work with these big players. We've had a follow-on grant with one of the world's largest automotive manufacturers. We know how to meet these industrial milestones. The linear actuator market, it's huge. $50 billion by 2022. So where does Hazel fit in there? Well, that's what we're working on right now. Like I said, we're a young company. Where can we take our key features of high power to weight ratio, fast, lightweight, silent, that we're soft and compliant to be adaptable, that we have direct linear motion and are quite cost effective? Our bill of materials for a single actuator is well under $1. Where do these features turn into customer values? In which industries? But of course, there's technical challenges along the way as well. We need to figure out our characterization more on an industrial standard. We can do it in an academic setting, but what about at 1,000 cycles, 1,000,000 cycles? And the electronics has some hurdles too. I'll get into those in a second. But my team's identified that we need to focus on mid-scale manufacturing today to address both those challenges. And speaking of challenges, where is this technology really? If we looked at NASA's technology readiness level, Hazel's currently at a 4, approaching a 5. We've definitely proven out basic principles, and now we're starting to make more complicated systems that work in relevant environments. With that, great time to spin out Artimus Robotics. But what's better yet is that we maintain a very close relationship with the Keplinger Research Group at the University of Colorado Boulder. They continue to do fundamental research to push the technology on a whole. It's fantastic. What's Artimus been up to since we started? Well, we've already had success. Earlier this year, we were at the University of Colorado New Venture Challenge, where we were fortunate enough to take home 2nd place in a pitch competition. And then just a few months ago, we were down at Denver, Ignite the Night, where we were fortunate enough to win 1st place and brought us to this stage here. But we're not just going around to pitch competitions. We're working on technical problems as well. The 1st generation of Hazel was all hand-built. Works great for an academic setting, not as appropriate for an industry setting. So we started to automate some of this. We took a 3D printer, hacked it together, and made some automated heat sealing. That's coming out in an academic publication soon. This helps address the lifetime and reliability. We've already taken this a step further, looking to turn this into a roll-to-roll manufacturing process that I would love to chat with you offline about. And I also told you we have some hurdles in electronics. 1st generation of Hazel used a refrigerator-sized $50,000 piece of test equipment. Again, what's the point of having a portable actuator if it's tethered to that? So we miniaturized our electronics. Reduce the size by an order of magnitude, reduce the cost by 2 orders of magnitude, and while we're at it, we also increase the electromechanical efficiency, currently operating at about 25%. These milestones have been fantastic. The research started in 2015. It's been moving quite nicely in the academic setting. Spun out Artimus earlier this year. We're funding it through a VC gift from our university. Our technology transfer office introduced us to some local VCs that actually gave a gift to the university. You don't hear academics talking about how great their TTO is too often. And also, I just found out last Friday that we're a finalist for a Colorado AIA grant that's going to help us move that mid-scale manufacturing further and develop development kits to provide our customers with test units. Some next goals. We've got to get the IP out of the university, of course. I've already started these negotiations. They're off to a great start. This isn't a concern. And we're doing this because we already have some great things ahead. I'm in advanced discussions with a corporate partner interested in making a seed or pre-seed investment around $500,000, contingent on getting that IP. And also, we're looking for our first sale. Through Accreta, we're hoping to sell to a government lab that's going to test our units in their environment. Again, love to chat with you offline about that. We're hoping that we'll have a minimum viable product and some revenues by the end of 2019, early 2020. We'll need investment to get there. How's all this happen? Because I have a fantastic team. I'm Tim, be finishing my PhD next month, and excited to be the CEO of this company. With me here today is Eric Acomb, lead engineer on this project. He's had experience in both startups and consulting for government labs. Shane and Nick are back at CU doing fantastic research to push the technology, and we're very fortunate to have a world expert in artificial muscles, Professor Christoph Keplinger, who's a Packard Fellow. So why am I here? Why NASA? Why Hazel? The good news is that's already happening. Hazel's been incorporated into a NIAC Phase 2 that kicked off a few months ago. And just last week, we sent up a Hazel technology into one of those microgravity planes to see how it performs. We're waiting to hear those results back. What could I use from you folks here? Well, from the NASA chief technologist, I want to hear about your unique motion challenges across your labs. Hazel provides some unique solutions, and I'd love to chat how we could work together. For any angel investors in the room, I'm looking for someone that wants to roll up their sleeves and get involved. Like I said, I'm looking forward to this corporate partnership that is looking promising late this year, early next year, and I'd love to have someone to come in alongside that to supplement that, both with business talent as well as with financial contributions. And then for the investors in the room, we are absolutely looking for corporate partnerships, both on the supplier and customer side. If you make thin plastic films, liquid dielectrics, electronics, or simply manufacturing equipment, I think we could make a nice partnership. And if you use an actuator, which I should have already convinced you almost everyone does, we would love to work with you too. Hazel Artificial Muscles will be a key component of the future of robotics and automation, and I'd love to take your questions. For sure. So the question's about environments. The question was about extreme environments in terms of temperature, heat, cold, radiation, NASA-relevant missions. This was definitely something that came up when we were brainstorming to integrate this into that NIAC program. In terms of environment, in terms of temperature, we'll start there. There's, like I said before, 3 key components: thin plastic film, liquid oil, electrodes. All of those individually have temperature usage designed for what we have here on Earth. We know that in space, it'd be very cold. That liquid, not going to interact so well. It's either going to freeze or it's just going to vaporize just because there's no pressure too. So that's something we'd have to figure out for sure. In terms of inside the space station, I'm not sure. For radiation, we've thought about that a lot as well. Absolutely, the materials we're using today for the consumer hazel might not be appropriate. One material we're extremely interested in looking into, though, is Kapton. We know that in NASA, you guys use Kapton for like a million things. We use Kapton all the time as well because of its great dielectric properties. And so we're looking to maybe use hazels with Kapton.
Okay, this is John. So I have a question. Just again, not knowing what it is, it seems like it's probably something similar to piezo, where it's a low current, but we use the voltages to actuate.
That's right.
So have you done any analysis to look at the overall energy requirements that you would need to do for like a robot to function for a day, and compare that to human muscles where we are relatively efficient?
Yeah, for sure. We absolutely have looked at that. In the initial academic paper that we published in Science in January 2018, we were asked to look at the electromechanical efficiency. And so we started there, and that's just monitoring your electrical signal in, your voltage and your current, you can get your power, and then monitoring how much mechanical effort it output. And for that, I believe we did 21% electromechanical efficiency. Theoretically, this technology would go to 80, but of course we're not there yet. Since then, we've already pushed the needle closer to 30, which is a great start. And then something we're doing in the lab right now, that's actually my last piece of my PhD thesis, is a full system efficiency. So out of a battery into mechanical motion, what's that look like? We're still looking into that. We're hoping it's going to be in the multiple percentage, which is actually going to be a pretty good start. But what I will highlight to you is that it's a very low power consumption. We brought a demo kit with us. It runs off a 5-watt high voltage output, and we never really are outputting more than 5 watts. So we have a completely portable system that runs on a cell phone battery, and it's a great start. That's where we're at today.
Okay, and then for everybody else, how does that relate to human muscles?
So I believe human muscles, you have to be careful. Human muscles are running on a chemical reaction, where our system runs on electrical. Eric, correct me if I'm wrong, but I believe human muscles are right around 30–35% efficient. Yeah, so we're approaching that pretty nicely.
Thank you.
Thank you.
Tim, I had a question regarding the IP ownership. Could you provide a little bit more clarification specifically around the university and your parent company and how discussions are going?
Yeah, for sure, and probably most of that's most appropriate offline, but as you're probably familiar, this was all based out of a university research group, and so that is the University of Colorado's IP, and there we are in talks to get the exclusive worldwide license for that. And I will say one awesome advantage is that we're a startup research group too, PhD student #1 right here. And with that, we were running off startup funds, and so there is no government money involved, and so it's just an interaction with the university. They're the ones who exclusively have rights to it. There's no NASA or anything else like that.
And there hasn't been any investment from private capital to date outside the VC group?
No, there has not been.
This is Tian Xu from Old Dominion University. My question is, did you consider the reliability, repeatability, durability problems for these materials and the devices?
So the question's about reliability, durability, lifetime. So Hazel takes a few different designs. You can make it with elastomeric systems. You can make it with thin plastic films. We've done some initial lifetime tests on both. The elastomeric ones we've seen go to over 1 million cycles, actually, and then we just stopped, ran out of time. The thin film ones are significantly less, and those are the ones we're moving forward with commercialization. So we're continuing to study that, but we need more devices. Big issue is that we're hand building them all, and then when I have a failure, I'm not sure if it's a fundamental failure of the technology or if Shane just had a heavy hand that day with the soldering iron. And so because of that, that's why we want to automate the entire fabrication process, at least to a high degree, and then we have reliable, consistent actuators that we can truly study. Furthermore, we've already looked at the ones that do fail. They fail through thermal failure of the thin plastic films. We've monitored it with IR cameras. We see where it's happening. We know which junctions it's happening on our heat seals, so we at least have an idea of where to start to attack it. So we're aware that we need to understand lifetime and reliability more. We're making progress towards it, but it's still pretty early and we need to do more work there.
Thank you very much.
Thank you. Yeah, fantastic question.
Is there, I mean, I know you're fairly early, but is there a specific actuator you're looking at the moment? Or is it a specific application?
A specific application?
Still pretty general?
Yeah, for sure. There absolutely is. We are early, but we've already had, I think I showed, we've had 28 customer contacts so far, which is a great start. I know we have a lot more to have. Two areas that are super interesting is the haptics area. So like I said before, Semitic Labs at the Denver event, they ran right up to us and said, how do we get our hands on this? And I said, let's talk. Because I think you've felt them. They're using that, haptics mostly use voice coils and things like that. It's not the most lifelike feeling. It's kind of like rattling. And so our soft compliant actuators interact with the human quite nicely. So that's one application. Haptic surfaces, morphing surfaces. We'll have to figure out some electronics to drive those. It's a little more complicated with all those different switches. But that's something we're very interested in. And then just the soft compliant gripper. Gripping is a huge industry. Robotics have been doing it for a long time. And there's a lot of delicate tasks that have remained untackled. So in the automotive manufacturing factory, traditional robots do a great job. They pick them up. But in fruit picking, not such a great job. And other soft robotic technologies like pneumatics and dielectric elastomer actuators do moderately well and have seen moderate success there. But we actually can go even lower force, which is an advantage. And so that's one area that we're very interested in as well.
Could you tell us a little bit more about your team and their skill sets?
In the team
In terms of Artimus, who is your team? What are their skill sets?
Yeah, for sure. So the team is the group of researchers, the principal inventors of the technology. And so, like I said, we're a brand new academic research team as well. I have experience at national labs before. I worked at Oak Ridge National Labs. And then I have management experience of being the lab manager for the research group. With that, they appointed me CEO. Like I said before, Eric was the first engineer to work on the Hazel project in the research lab. Does incredible work, has experience in both startups and consulting for national labs. Christoph Keplinger is a world expert in artificial muscles. And when I say that, there's actually a few other artificial muscle technologies. I mentioned them a little bit before, dielectric elastomer actuators and pneumatics. Hazel really is a combination of both those, and that's because he's worked in both those fields before for a while. Was at Harvard, where they do some incredible pneumatic research, have a spin-out company from there called Soft Robotics, Inc. We're not associated with them. That technology is moving forward as well. So it's great to have him on board. And then the two other scientists, Shane and Nick, are some of the most passionate people I know. They absolutely know the technology in and out. I wouldn't want anyone else alongside of us to commercialize. In terms of course, you recognize, we're lacking in our business sense, hence my ask for an angel that wants to get involved, and we're learning as we go.
Okay, this is John. I got another one over here.
Sorry, yes, sir.
Yeah, so have you guys started looking at, and are you capable of doing any real-time health monitoring, when you're going to approach a tear or degradation based on the electrical characteristics of the muscles?
So like health monitoring of the muscle, right? We have not done that yet. It's something we're very interested in. It's a great idea, especially because it is all just running off electronics. Electronics are relatively easy to monitor. We can check our current spikes, things like that. It's an approach that others have used in a peripheral field of dielectric elastomer actuators, and it's something we'd be interested in introducing as well. We haven't so far. Just to move a little bit further on that, we have done some closed loop control, really rudimental, and that will help kind of play into that a little bit when we're monitoring our voltage and our current signal, monitoring our capacitance in real time. We can incorporate that data for exactly what you're talking about.
Okay, and then also along the lines of health monitoring, so our self-healing polyimides, we have to apply a fair amount of heat in order to get them to self-heal. So what's the process for self-healing your fibers?
Yeah, for sure. That's a great question. So when we talk about self-healing, we had recognized when we started this in terms of the electrostatic actuators that electrical self-healing was the key component. So it's not a mechanically self-healing material. I've worked in that field before. Very interesting things. But this is electrically self-healing because that's the failure that was most common in this material. And that's where this idea of using a liquid comes into play. This has been a concept that's been used in high voltage transformers extensively. And so it's really just the idea of if you took a pebble and threw it through a puddle, that pebble is going to pass through the water, but after it does, the water's just going to reflow behind it. That's our self-healing mechanism as well. Electrical short through that liquid, dissipates, and then we continue to operate. We can jump to the slides. We've shown that self-healing over 50 cycles with certain Hazel designs. With certain ones, we're still working on that, specifically elastomeric versus non-elastomeric. But we know where the issues are when we're working on it. That's our self-healing. So,
hey, Tim, Andy Baer with Sway Ventures. Very
Andy.
Good presentation.
Thank you.
Very interesting technology. Can you tell us about where you think you want to take the company over the next 3 years? How do you see that developing?
Yeah, for sure. We're going big. We're going to manufacture. We know that it's extremely important to keep the manufacturing and technology as close to us as possible because there's so many unknowns. It's extremely young technology. That's why we're trying to do this, what we're calling mid-scale manufacturing, shooting to be able to make actuators on the scale of hundreds an hour. With that, as we grow over the next few years, we'll absolutely, like I mentioned this gentleman over there, need to bring in some business talent. It's definitely something, that's one of our holes, for sure. But we would really like to stay in that, I showed you before, in terms of products. We want to remain low complexity and a product that multiple different industries can use. So that way we can take the same product that perhaps we developed for the gripper and then put that in different verticals into the automotive industry, into automated manufacturing industry, things like that. That's where we hope to go with the technology. Over the next 3 years, it's going to take a while. Like I said before, I'm trying to be optimistic yet realistic about first product end of 2019, so over a year from today. But I know it's a hardware company. We've got a lot of challenges to tackle, and so I know that it will be a while, but I do hope absolutely to have a product going by year 3, like you suggested. Thank you. Sir?
How powerful are these actuators, and can they be linked together to make them more powerful?
Yeah, for sure. We can bring you force displacement curves at the tabling event later, but your question was, can they be linked together to make them more powerful? And absolutely. And also, because they're using hydraulic principles, you can scale kind of your active electrode area versus inactive other area in order to make them stronger but perhaps have less stroke. So you can customize them in multiple different ways. We almost always operate them in parallel today, and so we have a stack of 11 hazels operating together to get more total stroke. You could also, of course, parallelize them in series to get more strength or whatever you're looking for that particular day. Great question.
You had touched on your need for certain corporate partnerships. Could you repeat that need again? I know you went through pretty quickly.
No, for sure, of course. Corporate partnerships, we'll be looking for corporate partnerships both on our supplier side and our customer side. So in terms of supplier, we'd love some assistance in building out this manufacturing more. We know that that's where some of our reliability issues come from. And so those are, we use thin plastic films, we use liquid dielectrics, we have plenty of electronic components, and all the materials that manufacture around that. So any roll-to-roll processes, specifically in the heat sealing industries, but also any type of sealings, because we're essentially making pouches of oil. And again, we'd be happy to show you those. And then on the customer side, some initial customers would be in the robotic space, the Boston Dynamics, the Misty Robotics, the ABB, right? A company like that would want to help us integrate our component into their end design would be fantastic. But like I mentioned before, nearly every industry uses an actuator. But of course, we don't want to get distracted trying to dive into too many industries today, but we haven't set on one today either, so plenty of flexibility there. Does that answer your question? Great. Sir?
One of my favorite lines. Why did you choose the name Artimus?
Artimus, artificial muscles. We realized that a little too late. Great question.
So with that, I'm going to call time. Thank you, Tim.
Thank you very much, all.